Okay, so solving verification questions using machine learning. So this is the second part that Andy mentioned of the research I'm doing. So trying to use machine learning to solve verification. I won't really talk much about results because this is a story that has just started. So I'll try to give you the idea. I'll try to give you the intuition of what's going on. So the entire talk will be at the intuition level. So if you're into logics, I hope this will be boring for you. This means I'm not going very technical. If you're into machine learning, the machine learning part also will be boring. I hope that you grasp on the combination of the two. That's my goal, to show you how these two worlds can be combined in actually a very simple way. Okay, so let me start. So my background is more on the verification side. So I'm not an expert in machine learning. I understand a bit better the verification. So I will start explaining you what is verification, what are the questions that we are answering. Okay, verifying software is about ensuring that software is correct. Having machinery, a software that checks whether another software or a model of a system behaves correctly. And I'm sure it's not hard to argue how this is useful. It's definitely useful in software development. Think about a compiler that not only checks on your types, but also tells you whether your program is correct, whether you will never have a segmentation fault, for example. This is software verification. But this is not all. Compiler cannot do all the job. Sometimes your program that has been developed on a computer may be deployed on a server. And when it's on a server, there are other phenomena that occur. You might have requests that come in a probabilistic fashion. So you might want to make sure that your system is robust against a probabilistic model of requests. And you might not require that it's robust all the time. You might not require that it's robust, for example, to attacks. That would be too expensive. So you would like to reason in a probabilistic fashion about how your system behaves. Still, this lives in the purely computer worlds, but you can see that the questions are becoming a bit more quantitative, probability. It surely becomes fully quantitative when we are in cyber-physical systems domain. Your program is clearly interacting with a physical environment through sensors. Physics is surely a quantitative continuous, at least modeled as a continuous system. And another aspect of verifying software is not only with probabilities, but also software interacting with the continuous systems. And the question is, how do we make sure that software, when it interacts with these diverse environments, is correct? What does it mean for software to be correct, first of all? Normally, the question we think of is the safety question, avoiding that nothing goes wrong. So avoiding that your system goes in an undesirable configuration. This can be a server not finding a page. That's trivial, but it could be an attack. It could be a program having a buffer overflow, so accessing parts of memory that is not supposed to access, or simply crashing. This is one type of bugs, and it's the most intuitive one. So reaching a bad configuration, but sometimes there is another kinds of bugs that are a bit more subtle, where not necessarily something bad happens, but simply nothing happens. Your software gets stuck. Your program doesn't respond. And this is the dual of the safety question, is the liveness question. So is your system alive, or did it get stuck into a live execution that is useless, that doesn't do anything useful anymore? Now, when we're talking about software, this is we have experienced this software getting stuck. It might be in an infinite loop. We might be executing an infinite loop, but this is certainly also occurring in cyber-physical domains. Think about your self-driving car, which is controlled by an artificial intelligence, and your self-driving car doesn't crash. It's perfectly safe, but never reaches an appropriate cruise speed. It's so safe that it's going very slow. This for sure cannot create an accident, but you know, it can be very annoying when you are in the traffic. And it's not hard to convince you, I hope, that liveness bug, a performance bug in a system under certain circumstances can turn in a safety bug. Okay, so I introduced the liveness verification question because that's the question I'll focus on. So I want to verify, I want to make sure that systems perform, and I chose this to make the point. How do we solve a liveness verification question using machine learning? But machine learning could be used also for a safety verification question. But I'm focusing on this to make just to make a story. Okay, so liveness is what we want to prove. We want to prove that the system is alive. How can we look at the liveness verification question in a more specifically? How can we think of it? Well, we have think about a liveness verification question as the following. We have a system, and a system has an initial state, or more generally, a set of initial states, and a set of good states. Something describes what is desirable. And when we verify for liveness, we want to ensure that as the system executes, all possible states that are reached. So we look at all states after one step, after two steps, after three steps, and so on. All of them eventually end up doing something good. So the liveness question is whether your system eventually does something good. This is what we want to verify. To do all of this, so what happens? What happens when it doesn't do something good? So perhaps this helps understanding what is the liveness question. Well, a counterexample for it is an infinite loop. If a system gets stuck, if there is at least one execution that gets stuck in an infinite loop, is not alive. And what I want to argue here is how do we use machine learning to extract from a system a proof that the system is alive? All right, so I'll be even more specific. I'll introduce some notation, but that's really the whole notation I'm introducing. You have seen in the previous picture, that was a graph. And so all we need to keep in mind is this graph. That's the only data structure we'll use for the entire talk. Graph with the vertices that in this case are states. So we have a set of states and a transition relation. So a directed graph. Each node is a state, and a transition is a change of state. So that's how we describe a discrete system in general. A discrete system is not necessarily deterministic. So one state might have multiple successors. And that's what we want to reason about. A run is a sequence of states that satisfies this transition relation. This means every state in the sequence is a successor according to T, the transition relation. So there is an edge from state to state on the graph. And we say that a state transition system is alive if all runs hit a good state, or runs from an initial state if we want to restrict it. But fundamentally, what we want to ensure is that all runs, so the quantifier here is important. I want to stress on the quantifier. All of them eventually hit a good state, any good state. So a state that is in the set of good states. Now, how do we connect this with a program, a graph, a program? Well, we can think of the states as all possible configurations of the variables of the program. All configurations, all the variables of the program, all the possible configurations of the call stack, of the memory in general. And as the program executes, we have a transition, we have a change in the state, a change in the memory configuration. And what does it mean for a program to always hit a good state? Well, think about a good state as some set of these memory configurations, but fundamentally showing that all possible execution reach a certain configuration means showing that everything in between terminates. So if we have a program and this program is making calls to functions, and eventually we want to show that we reach a certain point in the program, point that we desire to reach, this boils down to showing that everything in between terminates. So there are no infinite loops. Remember, the counterexample to liveness is an infinite loop. This is why I will forget about liveness in general, and I will talk about termination. Okay, think about the good state as the terminal state, and we want to simply ask whether the program terminates. Why? Because we can reduce the one question to the other very simply. We can take the good state and then make the program return exit. Okay, so reaching a good state is fundamentally terminating. And so what I will talk about is does a program terminate? How do we use machine learning to determine whether a program terminates? Okay. If there are questions, interrupt me. All right, how is this normally done? Keep remembering about this graph. That's the possible configurations of the program. We want to this graph as some states that don't have successors, and want to make sure there are no infinite loops. How is this normally proven? Classically, how is this proven? By termination analyzers that are out there. This is normally shown by giving a ranking function. By giving a ranking function, the ranking function is the proof that the program terminates. What is a ranking function? Well, it's a function from states. So it maps states into a well-founded relation. Okay, so this means that we have this function that maps a state into some other set. And we want that every time there is a transition, there is a descent, we are descending along this set. Okay, so we have a set and an order here. And a mapping that satisfies this, and it is well-founded. This means that every possible sequence, so we see that this is mapping a state into some other object, and we want that this other object, all sequences, all descending sequences over this other object are finite. So there is this strictly decreasing, because think about it as an order, we are strictly decreasing, and we have a minimum. That's normally how it's shown. So termination of a program, so S is a state of a program, is shown by providing a function that has these characteristics. Now, this is I admit this is very mathematical, well-founded. What is this object? How do we get into machine learning? Let's restrict it into an example. Okay, this is a very general way of phrase termination, but in fact we will look into a specific example. Now we're not mapping into some arbitrary well-founded set. We're simply mapping into the integer numbers. So think about a function that maps a state into an integer number. And every time there is a transition, the value strictly decreases. And this function is bounded from below. So I know for sure that this function is bounded from below. And every time there is a transition, it decreases. So, now it's a bit easier to see, right? So we're getting closer and closer to the minimum since we are strictly decreasing. And it's integers here. So we're always strictly decreasing by an integer. Eventually we must hit the minimum, and we are guaranteed that there is no other successors afterward. Otherwise, the first condition wouldn't be satisfied. So that's the way we show we show that the program terminates in this case by mapping states into numbers, and these numbers decrease. Bounded from below, let's make it even simpler. Positive semi-definite. So a function that maps into the natural number, if you wish, but fundamentally it decreases, and it's a positive semi-definite function. So the program states two numbers, and it has these characteristics. A function like this exists, the program terminates. Okay, so you can see this object. This is quite classical, actually. So proving termination by providing a ranking function is the classical way to do termination analysis. And all methods, most of methods out there for constructing this function, they constructed by automated reasoning, by using some solvers that solve a combinatorial space of functions, and they compute this object. Then once you have it, you have proven termination. What is this object? Well, you can think of it as let's go back to our graph, as a function that gives you the upper bound of the distance to the good state. Okay, so we see that every time there is a transition, it decreases, and the good state cannot be less than 0, because the function is positive semi-definite. Okay, so mapping into the natural numbers and decreasing. Questions? No, yeah, no. All right. Okay, so now this is still, this is fine. This object is not yet ready to do machine learning, at least not that I know. Doing machine learning with integer numbers, natural numbers it's not the orthodox way, let's say. So we need to massage it a little bit so that we can do machine learning more comfortably. Okay, normally machine learning is done not on the integers but on the reals. There are models that come from statistics, and so they reason about a machine learning model is normally a model over the reals. Normally, I'm not saying always. And so there is a very easy way to modify this object. Let's give a function that gives a state, that from a state gives you a real number. And every time there is a transition, it decreases by a discrete amount. This discrete amount is a positive amount. So I hope you agree with me that it's fundamentally the same thing I said before. It's just, I'm asking for a discrete amount. So we're getting closer and closer to a minimum. Okay, so now we have decided what's the object we want to construct to solve this verification question. We started from a program, and fundamentally now we have to search for a function. A function that looks at states only. You see, it's only mapping a state into a value. That's all we need. It's really as simple as this. And solving the termination question, the halting problem, it's determining whether there exists a function. It's a search space. It's a search over a space of functions that have certain features. Okay, so I've shown you, I've modeled the termination analysis question into the question of searching for a function. But actually, something that we learn from machine learning 101 is that also machine learning is a search for functions. We're searching a classifier, we're searching a function, or we're doing regression, we're searching for a function. It's a search for functions. So machine learning in a very basic way can be seen as follows. Normally we have an input and an output domain. Classifier, the input is a set of pictures and the output is a set of classes. So that will be a classifier. But more generally, we have an input and an output domain. So the first question that we need to ask ourselves is, what is the input and output domain when we do machine learning? And normally this is solved by solving an optimization problem, so by minimizing over a loss function, by exploring a space of functions, so finding the best function that optimizes some loss. So we have a loss function that over a data set, so we will have a set of data, D here. Over a data set, it tells you what's the quality of this function. The higher the value of the loss, the worse the function that we gave is. Okay, so termination analysis, search for functions, machine learning search for functions. How do we make the first questions fit into this other? So now I will fill in the ingredients one by one. First of all, perhaps for the machine learning people, this is not so scandalous, but for a logician, it's like you're searching over special functions. It's very hard to do. In fact, what happens in machine learning is normally we're not searching for all functions that satisfy that type, but we have a parameterized model. So we have a parameterized model that satisfies that has this input and output domain and has some parameters. And what we do, we search for the parameters. Okay, so it's a parameterizer. So the search is a first order. So we're searching for a set of parameters. So we're restricting the space of functions. And the loss function, given the parameters and the data, tells you what's the quality of this function with respect to some objective, to the features that we want to obtain for this function over the data. Okay, so first thing we need to do here is filling in the ingredients, input domain, output domain. What is the data set? What is the loss function that we want? Let's start with input and output domain. So we already know what's the function we're searching for. We have declared it before, right? So we want a function that, given a program, it maps from states to reals. So input and output domain, it's simple to resolve. From states to real numbers. So we're searching for a model of this kind. And the next question is, how do we design a data set in a loss function such that we are collecting this data set, we construct this loss function, we minimize using our favorite gradient descent or our favorite optimizer. So we get this data, we optimize over this loss function, and we obtain a function that satisfies these two requirements. Remember, these are the two requirements of a ranking function. So how do we design machine learning problem this way? So there are two ingredients here we need to fill: data set and loss function. And actually, no, there is another one. What's the parameterized model? First of all, well, what can it be? A neural network. The parameterized model is a neural network, and why? Very powerful approximator. It works very well in practice. What is a neural network? Very quickly. Function. In this case, we want a function from states to a real value. Okay, so states. The state is what is described by the input neurons. So we need to model the input neurons so they describe the state. The state is the value of the variables of the program, for example. And there is a sequence of hidden layers, very standard. This can be anything. One output neuron, because we want one real value in output. So that's the kind of neural network we want. The input describes the state of the program. The output is one value. The network is, let's say, let's choose a fully connected architecture. What is the semantics of the neural network? Very quickly, let's focus on this neuron. One neuron is connected to a set of input neurons, and this happens layer by layer. Each of these connections have a weight. So X is the input neuron, are the input neurons. Y is the output. In this case, it's on that in that layer, right? And the connections have weights. the value of y is given by the linear combination of input neurons and weights applied to some activation function, which is normally nonlinear. Okay. So I assume most of you are familiar with neural networks, but just keep in mind it's a bunch of linear functions, one after the other, to which it also applies some nonlinear activation function. And in this case, as an activation function, I'm choosing ReLU. It's not arbitrary. There are technical reasons why we choose ReLU. The technical reason is because then we want to verify it also. But we choose ReLU. So, and I want to argue that also this has good properties for what we want to do. ReLU function, what it is graphically, ReLU function takes a value, the value of the neuron. If the value is positive, it gives you the value it has. If it's negative, it says 0. Okay, that's what it does. Okay, now all neurons have a ReLU activation function. This is already solving one of the problems we have. This is guaranteed to be positive, to be not negative. So actually the output domain is the non-negative reals. I hope this looks trivial so far because it has to. So a neural network constructed this way, not all neural networks satisfy this, but a neural network constructed in this way will always give you a non-negative number. And this means that we know what is our parameterized model here, a neural network. We know what we want to obtain, but this means that already one of the two constraints we can forget about because it's guaranteed a priori. A neural network will always satisfy the second constraint of a ranking function, being bounded from below. So all we have left to think about is that it decreases at every transition. That's all we need to think about. So now we have to design a data set and a loss function such that after we train, we get something that decreases. That's all we need. So the problem got even simpler because one of the guarantees that we want to ensure is guaranteed a priori by the model. So we have transferred this being bounded from below into the model. So the model guarantees it always. Cool. All right, so dataset and loss function. What is the dataset? The dataset is a sampling of the transition relation. And the loss function takes a sampling of the transition relation. So these are pairs of consecutive states. So every two states connected by an edge in the graph, pairs sample randomly in this graph, in the state space of the program. And the loss function fundamentally punishes if you're not decreasing by an epsilon. So that's what this function does. The loss function takes two states, applies the same model to both. So now the model appears twice in the loss function. This is the same model appearing twice with the same parameters. And we want that this model, if it's applied to two consecutive states, it descends by epsilon. So this punishes if this doesn't happen. Okay, so this is how the loss function looks like. What is a finite sampling of the transition relation? How do we obtain this data? Where does it come from? What does it mean to take any two consecutive states? Testing. Execute the program and look at the states. Run, execute it. Take many different tests of the program. As the program runs along these tests, as the program runs, we are observing the values of the states at every step. We will have pairs of consecutive states. So the dataset is obtained by executing the program. Okay, so now we have all ingredients in place. We have a loss function. The loss function enforces that the same function applied to two consecutive states decreases. We know what is a data set, very simple to obtain. Run the program, just take executions of the program. They don't have to be all of them. As many as you can. The more data you have, the better it is. Execute the program, observe the values of the variables, and train this function using your favorite gradient descent tool. Okay, but this is not the end of the story. So if we train this object, this is not guaranteed to be a ranking function. If we're lucky, it is, but it's not guaranteed. How do we guarantee it? To guarantee it, we use a framework that first consists of training and then verifies the neural network, as opposed to the traditional machine learning workflow that has a training phase and a testing phase. Here we're substituting the testing phase with a verification phase. As it happens in software engineering, those that are very familiar with verification is a more powerful testing, if you wish. It's a testing that is formal and attempts to try all possible input values and not only a larger set of input values. So we have this modified machine learning framework that trains and verifies instead of training and testing. So what happens? 3 phases. First, we collect traces. So we execute the program. We get this data set. Then we know what is our loss function. We know what our machine learning does. It will train this along multiple executions. In this picture, there is only one execution, but think about multiple of them. It doesn't matter how many we take. What matters is that we have pairs of consecutive states. We'll make sure that the neural network decreases along every pair. Now, fine. So we optimize our ranking function, and what we obtain is, let's say that optimization went perfectly, our loss function has been brought at exact minimum. So I'm making this assumption. Yet, this is not enough, because we will have something that behaves as a ranking function over the data and not over the entire program. So over a sampling of the transition relation. But you remember that what we want is that it decreases by a discrete amount over all possible transitions. So this is not all. So we training will give a function that behaves as a ranking function over all sample transitions. And what we can do after that is to check whether this also decreases over all possible transitions. And here we're exploiting a very interesting observation. Checking is much easier than checking a ranking function is much easier than finding one. Previously, finding a ranking function was done by reasoning methods that were trying to construct, not necessarily one shot, but tries to construct using formal reasoning, a function that satisfies these requirements. And constructing it is not so easy. While checking that a function decreases is much simpler. It's much simpler to do using automated reasoning. This can be done by an SMT solver. And so what happens? First, we train the ranking function using classical machine learning. Then we check whether it decreases, and this is easy to do. If it decreases over all possible transitions, we are happy. The program terminates. Otherwise, we can't say anything. If it doesn't decrease, we can't say anything. Now, the question is, does this work in practice? Because if the machine learning system trains our parameters, and then the verifier is happy with these parameters, then we have proven that the program terminates. Does this happen in practice? This is the first question we need to answer experimentally. Other ideas could arise. An SMT solver could propose a counterexample, and the counterexample could be used to train no data, to get new data for training. So this can be augmented into a system of adversarial training, where the part that trains the neural network and that tries to validate it are playing against each other. And this is fundamentally the picture. That's the point I wanted to make. I go through a few examples if I have a bit of time, But that's really the message I wanted to bring across. Okay, so we have played with this idea a bit. Training a candidate, not being sure the candidate is right, and then verifying and hoping it's right. We've done this with Java programs. We have done this with Java programs. The paper is Neural Termination Analysis. Quick example, let's imagine about a while loop that increases up to bound. This terminates. You can see this terminates. How do we prove it? We want to prove it automatically using machine learning. Well, first we execute it with multiple inputs. We execute it with multiple inputs. For example, we start with 0, 4. We'll see that 1 increases up to some bound. We may have a value that doesn't even enter the loop. It's fine. We collect plenty of these, and we take every consecutive pair. It doesn't matter whether they're in order or not. It's not along one trace, but it's along every pair that we are training. We train, and that's the function we get. ReLU of n minus I decreases, because I is getting closer and closer to n, and it will never get negative because you exit the loop. So machine learning will give us this very simple neural network, but it's a neural network. And then we verify whether this is true. It means, we want to verify whether for all possible states, if we apply the transition, then the function always decreases by a discrete amount. I should have written, but yeah, always decreases. So we are asking this validity question using SMT solving. Quick parenthesis, how is this done? Using SMT solving, this is a validity question. This means we want to check whether every two possible states, so pairs of states also here, that satisfy the guard of the loop and satisfy the update. We want to make sure that all of them satisfy the decreasing, satisfy that the value decreases. How is this done with an SMT solver? For those that have used SMT solvers before, this will look simple, but just to make sure it's clear, this can be turned into a SAT question. So it's a validity question. We want to ask something for all. We phrase it by asking for a counterexample. Does there exist a counterexample? So does there exist a value that behaves according to the program? This is what it says, but doesn't decrease. If one such value exists, then this is not a ranking function. Otherwise, we're happy. And this can be done by SMT solving. Using a ReLU is not only for the bound from below. So that's an important component, but having multiple hidden neurons is actually helps finding nice termination arguments for slightly more complex programs. For example, this tiny program requires a network with 2 hidden neurons. We have made a few experiments with this, and it turns out that for a good chunk of classic examples from the termination competition, a few hidden neurons suffice to solve over 75% of all programs. And keep in mind that solving the 100% of this problem, which can be solved by the state-of-the-art tool, has taken 20 years of research. So it's these tools are very sophisticated. We got the same result using this very simple method, which really requires very few lines of code. It's really sample the data and apply that loss function, no more than that. So an almost naive implementation could get to 75% of what the state-of-the-art can do. How we sample the data matters. I won't go in this. And well, we have applied this also to program with data structures. This is nice because it can discover termination arguments also in more complex programs. Another thing we have done, we have extended this to probabilistic programs. And here we go into the non-determinism, right? Is it deterministic? What is a non-deterministic program? Could be a probabilistic one, where the successor is sampled. There, the termination question changes slightly. Then we ask for the almost sure termination question, and we need a different kind of function. it's not a ranking function anymore, but a ranking super martingale, which means it decreases in expectation instead of decreasing always. This shows that the program terminates in almost in expected finite time. And I've showed you before how to do this with deterministic programs, and now we know a bit the game, so we can apply it. We can modify our loss function so that it descends in expectation. And going quickly, some modification in the loss function. Now we want to talk about an expected value. So this means taking the average, taking a bunch of successors and taking the statistical expected value. What is it? The average value. So if the average value of the function decreases, then this is ranking super martingale. We have compared this also with the state of the art. It turns out that even though we are slower than the state of the art, in this case, we can solve more problems. And this is due to the fact that our method for learning the ranking function is agnostic with respect to the program. It doesn't need to know anything about the program. It only needs to have this testing set. So these data that are sampled. And also it exploits the fact that checking, because that's all we have to do, is easier. Since checking is easier, we can solve more problems. So all the problems under this line are problems that we can only solve, and the state of the art cannot. So this is interesting, even though we're not as fast as they are. We have applied this to stability analysis. What is a ranking function when we want to do stability analysis? Lyapunov function. I'm sure you guys are very familiar with Lyapunov functions. So instead of saying that it decreases, the derivative is negative, and the value is bounded from below. Same argument. We can guarantee it's bounded from below, and we only need to take care of having a network that is negative derivative everywhere, negative gradient everywhere. Also slightly modified loss function. We have played with this adversarial learning in this case, where counterexamples are fed back to learning. And this is a graphical depiction of what happens. So we first try Lyapunov function, we find a counterexample, that's that little x. Then we add this counterexample to the data set. The Lyapunov function gets refined, so it gets better. So this is the domain, this ellipse is the domain. And as we find counterexamples, slowly, training will make it become a good Lyapunov function, where the value, the gradient is negative everywhere in the given domain. We have compared this with other similar methods that also use neural networks, other similar methods that use other templates, and with SOS tools too. And it turns out that we can solve, we can find Lyapunov function for the widest domains with respect to the state of the art. Still, we're not the fastest, but we find better Lyapunov functions. And those with respect to SOS tools, which is the state of the art, we can give formal guarantees, and they cannot. In general, that's unsound. Now, wrapping up, same method applied into 3 different domains. We can call this a neurosymbolic method because it combines neural networks and symbolic reasoning for Liveness verification. And we applied this in 3 different domains: deterministic programs, probabilistic programs, and dynamical systems, each of which have their own witness of termination. For deterministic program is the ranking function, for probabilistic program is the super martingales, and for dynamical system is the Lyapunov function. And here the idea is, we know what these 3 objects are, let's use a neural network to model them, and then train the neural network. Conclusion, what is the main intuition that we're exploiting here? We're exploiting the fact that checking a proof is much easier than finding one. Therefore, first guess a candidate proof using a powerful, yet not necessarily formally sound, but a powerful method, machine learning, neural networks, and then limit the formal part only to the checking. And this is it.